Go ahead and get started on the bell work. Take 30 seconds, see if you can solve this one here. Now, this one is a function, and the first thing we should notice here is that there's no x values that repeat, so automatically this one would be a function. All right, there's our objective. Just take 30 seconds to write this down. I can write the equation for a function. All right, equations for functions is still going to look like slope-intercept form, right? So you got y equals mx plus b, like this. Now, we learned last time that if you can write an equation in slope-intercept form, you can write it in function notation, which has the only difference of f of x right there instead of y. Because this would indicate that the function is depending on x, and we'll get more into dependent and independent variables today, because you'll need to know the difference. Now, the y-intercept, if we look at a table, no matter how it's set up, in order to find the y-intercept, you're just looking for where the x value is 0, and then its corresponding y value there, b, that's the number that you'd put into this blank, if it's right there. Now, m, it's the slope, but since we're going to be seeing some word problems today, it's also considered rate of change. So rate of change is the slope, and if you can find the rate of change, you can just insert it directly into the equation right there, all right? Now, rate of change is built with the y values in the numerator and the x values in the denominator. If we see it, whether it's written as a fraction or the rate, doesn't matter. Like miles per hour, right? Miles would be in the numerator, then hours in the denominator. That would tell you right away which one is x and which one y. Because once you know which one is an x and which one is a y, that tells you which one is independent and which one is dependent. Particularly, the x value is considered independent, which we'll get more into. And the y value will depend on the x value. All right, that may be some science stuff that you've gone over before, whether you remember it or not, or whether you actually have or not. It doesn't matter, because we're going to be going over it today. But this will be important. You may not see it as a rate like that. For example, miles per hour sometimes is just written like this. But if you can notice where the rate is, then you can know the rate of change pretty quick. So Paradise Valley Orchards has the banner shown hanging from their store window. Sally is trying to determine how much she will spend depending on how many bushels of apples she purchases. Write an equation that gives the amount Sally will spend, y, depending on how many bushels of apples she purchases. So they already told us what the y and x's are. So the y is the dependent variable, right? Y, that's how much she spends. And it even used the word depending on this one. So spending, that's y. And number of bushels, that's the x right here. So this is what it says. 1 bushel of apples for only 15 bucks. All right, so if we wanted to write the equation for this, it would be y equals mx plus b. We just got to fill in these blanks right here. So if we can find the rate of change, and in this case, it's actually a unit rate. But here's what we know. Remember, it's always written as y over x like this. And they said y is dollars spent, and x, that's how many bushels she purchases. So I'm just going to write bushels here. And what values did it give us? Well, it said it was down here. It's $15 for 1 bushel. So this is what it would look like as a fraction, all right? $15 per bushel. But we could simplify that directly into the equation and just make it 15 right here. So right now it shows y equals 15x. The next thing we need to do is find the y-intercept. Now the y-intercept would be how much it would cost for 0 bushels. And yeah, it doesn't indicate that there's any kind of fee on this thing, so it would just be $0 for 0 bushels, which also represents the origin if we graph this, which we're going to. Now, just so we understand as well, I believe on the assignment it does not want the phantom zeros right there. So the final equation for this one would just show y equals 15x. And yes, this could be written as a function as well. The function, the y value, will depend on the x value, and this is just written as 15x. So that is the equation and the function notation. Now we have the equation there at the bottom, y equals 15x. We already know x is bushels of apples and y is the amount of money spent. And in fact, they put those in the table for us, which is very generous. However, it did not give us x and y values specifically, so we're gonna have to use or just put in our own x and y values. Now there's a couple questions that may come up, and that is, can we go in the negatives for the x? Now generally speaking we could, but for a word problem like this one, it wouldn't make sense to have negative bushels of apples. I don't know exactly what that would look like, so we're not gonna go into the negatives. The other thing we need to consider is, can you have partial bushels? Well, it didn't say that you could. It's just one bushel. Whether you put, or there's like it's half filled with apples, doesn't really matter. It's still going to charge you 15 bucks. Okay, so if you bought a bushel, no matter how full it is, it's still going to be 15 bucks. So the other value that we need to consider is always 0. And just like we saw with the objective, we want to look at 0 because this is the y-intercept. So once we figure out how much money this will cost, that will tell us the y-intercept on this one. And of course, 0 bushels, they're not going to charge you anything if you don't purchase any bushels for this one. Now do keep in mind there are situations where they will, right? Like usually for math classes, it's like a gym fee or like one of those bulk stores like Costco or Sam's Club, something like that. All right. Now next up, it says 1 bushel, and I'll do the work over here actually. So here we got the equation, y equals 15x. And right here we're saying the x value is 1. So I'm going to replace the x value with 1 and solve for its corresponding y value. So that's 15 times 1, which is 15. So when you buy 1 bushel, it would be 15 bucks. And in fact, I'm just going to look at 1 bushel each, 1 additional bushel for each of these. So I'm just going to go up to 4. Now you could use other values if you'd like, but I think this is a little bit, I don't know, more clear. It's at least more clean on this one. So next up, I'm going to go back to the equation there in the top right, and I'm going to replace the x value with 2, and 15 times 2 is 30. Now some of you know the pattern, right, because it's just $15 per bushel. So if you say, I know it's another $15 here, here, and here, okay, that's fine. I'm going to continue to use the table just so we can see it, because we're going to see examples like this on the assignment as well. So the next value is 3 bushels, 3 times 15, $45. So 3 bushels, 45 bucks. And then the last value there, 4 bushels. So I replace the x with 4. 15 times 4 is 60 bucks. So if you purchase 4 bushels, you're going to pay 60 bucks. All right, and this would be the table. And even though we know that the equation can be written in function notation because it's written in slope-intercept form, the table again shows that the x values do not repeat, so this would be a function as well. And so we should expect to see that the graph will pass the vertical line test as well. But the first thing we need to do with this graph is to label the axes. And down here it said that x was bushels of apples, so I'll start with the x-axis. I'll just put bushels. And then the y-axis is amount spent, so I'm just going to put a money symbol there. That's how much it will cost. So that labels the axis, but we still need a scale on the axis. And we should really start with 0 for both axes, but I'm going to start with the x-axis. And since in the table I just went up by 1 bushel for each of the rows, I'm going to make each of these lines go up by 1 bushel. So that'd be 1, 2, 3, 4, 5 bushels. 6, 7, 8, 9, 10 bushels. Right there. Now, just like we did last time with our graphs, we'll be a little bit methodical about this one. So we'll say, okay, I know it's $15 per bushel, and it's going through the origin, in fact. So if I just make each of these lines go up by 15, then all of the ordered pairs will fall directly on these gray corners, all right? So this would be 15, 30, 45, 60, 75. There's 5 lines. Let's see, 90, 105, 120, Never good with my 15 times 10. 135, and then 150. Then 165, 180, 195, 210, 225. Right there. All right? Now you don't have to label each line, but it's good to see every fifth line labeled. That'd be nice. And now we can put these ordered pairs on the graph. So I got 0 bushels for $0. That'd be this point here. And then 1 bushel for 15 bucks. Again, each of those lines represents $15. So again, that's going to fall right on that grid corner. And then 2 bushels for 30, 3 bushels for 45, and 4 bushels for 60 bucks. Creates this graph. And it is true that we can see the pattern in this graph, so I can put the other points on there. 5 bushels would be 75, and then it's kind of like we're using the slope to find all these other points. Now we have this lined up, and the last thing we should do when we make our graph is ask ourselves if we should connect the points. Well, that goes back to if you can have halves of either bushels or dollars. So I'd start with the bushels. I usually start with X, but I'd say, could you buy half a bushel? And the answer is no. It did not say that you could. So I would say we're going to keep these separated as points, like this, okay? Now there will be situations where we have to connect the line. But just so we understand as well, when you do not connect the line, this is what we call a discrete relationship. So this is discrete, which isn't so important in 8th grade math, but it will be in 9th grade math. And the last thing we can do on this is confirm that this will pass the vertical line test, and it will. There's our vertical line. I'm going to take it and scan it. There we go. And we can see that there's never 2 points on this green line like this. So it's still a function this way. Last thing I want to go over on this one is domain and range, because we're going to see that on the assignment for this one. So the domain and range on the assignment, it wants you to list these from least to greatest, and it should already have the fancy brackets included. Now your domain could be different if you use different values than I did, but the ones that I have is 0, 1, 2, 3, and 4. And again, it wants at least written from least to greatest. So the domain is just all the X values. That's this column right here. And then the range is all the Y values. Fancy brackets is just this column, these values that I got. So 0, 15, 30, 45, and 60. Just be careful, because if you see negative values and it wants it from least to greatest, the more negative it is, the less it is. So it may not be matching 1, 2, 3, 4, 5 on this. We know from the previous lessons that the relationship between number of bushels purchased and the amount spent is an example of a function, which we just saw. That was a functional relationship. The equation above gives us the rule for how to determine the amount of money spent based on the number of bushels purchased, which was y equals 15x. But again, we could write that as a function notation, f of x equals 15x. So in the functional relationship represented with an equation, the independent variable represents the input or x value of the function, and the dependent variable represents the output or y value of the function. In a function, the dependent variable is determined by or depends on the independent variable. In our example above, the independent variable is the number of bushels purchased, and the dependent variable is the amount of money spent. The amount of money one spends depends on the number of bushels one purchases. Another way to say this is that the amount of money spent is a function of the number of bushels purchased. So again, one of the words we're kind of looking for here is it may not use the word depend, but we went over this last time. It's always going to be y is a function of x, right? So that's why money is y right here, and x is the number of bushels purchased. But another word you'll look for is either depends or based. So if something depends on something else, then it's the dependent variable that something is. If it says it's based on something else as well, then it's still dependent. Now, if we think about our input machine, we're inputting the number of bushels purchased, and the machine that takes and multiplies it by 15 gives us our output, which is the amount of money we will spend. Yeah, so back in the day, they used to use these function machines like this, which had a little smokestack, and it would pump out steam or whatever it is you wanted to think that it pumped out. And it had a conveyor belt right here. And yeah, I know some of you guys don't know what a conveyor belt is. But either way, you'd have the input going into the machine. And if we remember from last time, the input, that's the X values, which is the domain. And then it's going to bring something out, so that's the output, which is the Y values. Well, then they'd say, okay, it's got a function in this, and that last one would be 15x. Sometimes they'd have windows, and then they'd have little fun animations in the windows, so pretty. But like if I said I'm going to put in a 1, which would be 1 bushel, then you'd say, okay, take the x value, multiply it by 15, 1 times 15, boom, it'd be 15. That's the output, and then you'd label it because we knew it was $15 per bushel. Or if you said it was 2, you could even say 10, right? I'm going to put in 10. Well, 15 times 10 is 150. And so 10 bushels would be $150. And, well, it was pretty, but maybe it's outdated now. So Miguel's taking a road trip and is driving at a constant speed of 65 miles per hour. He is trying to determine how many miles he can drive based on how many hours he drives. Now, we should be able to figure out the independent and dependent variables just from the rate that it gave us, which in this case is unit rate, 65 miles per hour. But if we didn't see that, then we could just look for one of the main words which will tell us it's dependent. That's based in this case. So how many miles he can drive is based, which means it depends on something else. So that means how many miles he can drive is the dependent variable. We can put that in right there. It will always depend on the independent variable. And what was it depending on? How many hours he can drive. So I'm just going to put hours. You can put hours driven if you want to be more specific, but that's hours, which is independent in this case. At 65 miles per hour, that's just written as a rate like that in a word problem. But if you were to write it out as a fraction, it would show 65 miles per 1 hour, like this. And again, the top is always the Y. I use corresponding colors here, which is the numerator. And the denominator is usually the X in a rate like this, okay? And this would tell you, as long as you know Y is dependent and the X is independent, if you saw it as a fraction like this, you'd know very quickly which one is dependent and which one is independent. So now that we know which is independent and which is dependent, when it asks for X and which one's Y, remember the X is independent, and that was hours for this one. And the Y value is dependent, which is miles for this one. So Miguel, he's going 65 miles per hour on this road trip. And we'll get to the equation, but let's finish the table first. And again, you wouldn't go into the negatives because I don't know what negative hours looks like. But besides that, we should only be in quadrant 1 for this type of word problem. So 0 hours. In fact, I'm just going to go by 1 hour each. So 1, 2, 3, and 4. And again, you could ask yourself, well, could he be driving for half an hour? And yes, he could. In fact, you could have half a mile, which is going to indicate that we could connect the points on this graph, which we're going to do. But what I do know is he's driving 65 miles per hour. So at 0 hours, he would have driven 0 miles right there. After 1 hour, well, at 65 miles per hour, how many miles would he have gone? 65. Now for 2 hours, he's going to go another 65. So 65 plus 65 is going to give us 130. And then if he goes another hour, that's 3 hours. So 130 plus 65, 195. And then finally 4 hours, that's another 65 miles. So that's 260 miles in 4 hours. All right, so that creates the table. And again, the domain for this would be 0, 1, 2, 3, and 4 for the values that I used. And the range would be in fancy brackets 0, 65, 130, 195, and 260. But let's go ahead and make the graph for this, then we'll write the equation. Well, we know X is hours, so that's the label for our X-axis, hours. And the y-axis, that's dependent, and in the table that's showing as miles. So miles per hour. And now I'm going to scale the graph, and we should always start with 0 on these both axes. And once again, I can see in my table, it's just going up by 1 hour each time, at least the way that I made it. So for each of these lines, I'm just going to make it 1 hour. Going all the way up to 10 hours. And then once again, we'll be a little bit more methodical with scaling our y-axis on this one. And since he starts at 0 miles for 0 hours, which is the origin, if I just make each of these lines represent 65 miles, then each of the ordered pairs will land on a grid corner. So that'd be 65 there, 65, 130, 195, 260, and then that'd be 325, looks like. I think I did that right. And then another 1, 2, 3, 4, 5. There's 10. So that'd be 650 there. 1, 2, 3, 4, 5. Be another 325. So that's 975 at the top. All right. And again, I don't need to necessarily worry about what each of these values is because he's going 65 miles per hour starting at the origin. So I would put a ordered pair at the origin here. And then 1 hour, 65 miles. Again, we've set this up so that it should just be one line, which is 65 miles, for 1 hour. Another 65 miles, another 1 hour, or 3 hours, 195, 4 and 260. And again, we should be able to find the other ordered pairs on this because of the pattern that we see. So these are the ordered pairs. But the last thing we should do is figure out if we should connect these points. Well, you can. He could be driving for half an hour, and we could figure out the exact mileage for those partial values, which means that we will connect these points. I kind of missed on that one. That's okay. So this connects the points, and this relationship then would be considered continuous. This is a continuous function. Continuous. All right, so discrete is where we do not connect the points. Continuous is where we do connect the points, which again, if you were to zoom in on this, would indicate that every point on the line would be a true statement. Like this one, that'd be a half an hour, and then it'd be half of 65 right there. And yeah, he could go for that half hour, and we can figure out that distance as well. So the last thing we need on this is an equation. So it should be in slope-intercept form. Y equals mx plus b. And we can see either through the table or through the graph that the ordered pair there is just 0, 0. So it'd be a plus 0. And since it is plus 0, I'm going to make that a phantom 0 right there, which means all we need now is the slope, which is the rate of change. And the rate of change on this one is 65 miles per hour here. So I'm just going to put 65 there. Y, the distance, or the miles he goes, is 65 times x, the number of hours he drives. And since this can be written in slope-intercept form, we could write it as a function. F of x equals now 65x. And then is this situation a function? Is in this situation, yeah, we would say that miles is a function of hours. Yep. Guess those are blanks. All right, so we just showed example of discrete functions and continuous functions. Again, discrete would be where you have maybe a pattern like this one, but you're not going to connect the points. Continuous is where you have points like this, but then you do connect the points. Okay, discrete and continuous. It's that easy. The average cost of a movie ticket has steadily increased over time. We need to just, all we need to do on this one is to figure out which one's dependent and independent variables on this, okay? So, the cost of the movie ticket has steadily increased, which means that the price or the cost is depending, right? It's happening based on time right here. So the average cost, that's our dependent. It's depending, the cost is depending on the time. Yeah, maybe I should just put dependent. But I don't know that there's any key words on this one. I mean, it says that the cost, and this may take some thought on your part, which means that these aren't so instantaneous, but we should think, oh, the cost is changing. The cost is increasing in this case. Over, I guess over would be the main word that makes this dependent. Over would make it, because as a fraction, this would be cost over time like this. And we already said, remember, your y's are always on top, x is on the bottom. And y's are dependent and x are independent. So here's, what is that, 6 more examples. Each of the following situations represents a functional relationship between two quantities. Determine the dependent variable and the independent variable. All right, so I'll kind of color code these. I'll make my dependent variable in green and the independent variable in orange, like this. I'll still label them with an I and a D, but I won't write the full word out. So in number 5, in warm climates, the average amount of electricity used rises as the daily average temperature increases, and falls, the daily average temperature decreases as well. So the two things we're comparing on this one is we're looking at electricity used, and also temperature, right? And again, you may think about this, the electricity used, is that depending on the temperature, or does the temperature outside depend on the electricity you're using? Well, hopefully that makes sense, that the electricity used will depend on the temperature that it is. So temperature is independent in this case, and the electricity used is dependent. Again, it's a matter of which one depends on the other. So number 6, the number of calories you burn increases as the number of minutes that you walk increases. So the two things we're comparing on this one, we're looking at calories and number of minutes walked. So will calories depend on the minutes you walk, or will the number of minutes you walk depend on the calories you burn? Well, one has to come before the other, is really kind of what we're asking here. And so you got to walk the number of minutes, and then that will determine how many calories you burn, which means that the calories is dependent and the minutes is independent. And again, we did talk about this. If you ever see some form of time, it's usually independent anyways. No matter if it's minutes, days, years, eons, doesn't matter. Usually, unless it's worded very specifically to make it dependent, it usually is always independent. So number 7, the air pressure inside a tire increases with the temperature. So two things on this one, air pressure and temperature. Now when we say temperature, we're looking at temperature outside, I assume. It could be the temperature of the tire, I guess, which still should depend on the temperature outside. It increases with, so it means that as the temperature increases, then the air pressure may increase as well. So that makes the air pressure dependent and the temperature independent on this one. There we go. And then number 8, as the amount of rain decreases, so does the water level of the river. So this one, it's kind of going to work backwards based on what we've been looking for. But we have the water level of the river, and we have the amount of rain. Okay, hopefully that makes sense, that the water level of the river will depend on the amount of rain that occurs, which means that the amount of rain is independent, and the water level of the river is dependent in this one. Then number 9, the total number of jars of pickles that a factory can produce depends on the number of pickles they receive. So two things, we got number of jars of pickles the factory can produce, and then also number of pickles they receive. So jars, you could say, and just number of pickles. But the number of jars will depend on how many pickles are in the factory on this one, which means this one here is dependent. Number of pickles they receive is independent. dependent, independent. And then finally, number 10, the weight of the box increases as the number of books placed inside the box increases. So again, the weight of the box is going to depend on the number of books inside the box. So the weight is dependent and the number of books is independent. So a function is a relation in which each member of the domain input value is paired with exactly one member of the range output value. You can organize the input, rule, and output of a function using a function table, which we've done. This is just a table. But remember, you're just looking for any x values that repeat. If they don't repeat, then it's automatically a function. If they do, then you got to look at their corresponding y values, which is what this is saying, just in more nerdy terms. So this one, the only thing I want to point out on this one, I know it didn't print on the worksheet, but remember the left column, that's the x values, the input, that's the domain. So this would be -1, 0, 1, and 2, which we see down here. And then the output, 2, 4, 6, 8, boom, that's the range. The right column is the range. So that's 2, 4, 6, 8 in fancy brackets. So evaluating functions like this. So on this first one, remember whatever number's in the parentheses right here, that's also the x value. So I'd say, okay, this is really f of 1 right here. See how the x was replaced with 1? So this x I would replace with 1 as well, and then I would solve this function, right? Which is really just 1 plus 3, which is 4. So this is f of 1 equals 4. And that's how you would solve something like this. Whatever's in the parentheses, you replace into the equation, which we saw in the last assignment, which is good. But in addition to that, you'll want to know that this gives us the ordered pair 1, 4, right? 1, 4, x is 1, y is 4. So we'll do that on this next one as well. But now it's f of 6 instead of f of x. So that's 2 times 6 right here. And 2 times 6 is 12. So f of 6 equals 12. And just once again, this could be written as an ordered pair, which would be 6, 12. So function notation like this is nice because it does give you the ordered pairs directly, which kind of eliminates the need for a table, although you could make one still if you needed to, or if it asks for one. All right, this next one, it's f of 4. So we're going to say x is now 4. So now that'd be 5 times 4 minus 4. And 5 times 4 is 20. Still minus the 4 there, though. So finally, f of 4, 20 minus 4 is 16. Which again would be the ordered pair, 4, 16. Now I showed this extra step. You could have just typed in 5 times 4 minus 4 in the calculator and would have given you 16. But sometimes it's good to see that work right there. So this next one, f of 9. So f of 9 equals -3 times 9 plus 10. And again, you could put this directly into the calculator. And if you did, it would give you -17. Which again, that's another ordered pair, 9, -17. All right, these last two, that's f of -2, so f of -2, once again, just put that into the calculator. 4 times -2 minus 1, and it will tell you what f of -2 is. Looks like that'd be -9. So this gives us the ordered pair, -2, -9. And then this last one, f of -5, so replace the x with -5, so that's -2 times -5, plus the 8 right there. Put that in the calculator, that will tell you what f of -5 is, which appears to be 18. So that's this ordered pair, -5, 18. Kind of quick. So this one, it gave us open boxes in the table, so we can choose our own values. And in this one, since it's not a word problem, you could choose negatives, but I'm going to avoid that just because I can. So on this one, right, it's f of, this would like be f of 0 right here. So you'd say, okay, 0 minus 10, that's negative 10. Or this one, that'd be f of 1. So that'd be 1 minus 10, which is negative 9. And then this next one, f of 2 right here. So that'd be 2 minus 10, which is negative 8. And so this next one, 3 minus 10, that'd be negative 7. So when they ask for the domain and the range here, D for domain, R for range, some fancy brackets. The domain just has the values 0, 1, 2, and 3. And then the Y values, this is still listed from least to greatest, but be careful with those negatives, even though this one got put in order. So that's negative 10, negative 9, negative 8, negative 7, because on assignment, it will ask for this from least to greatest. So about number 8, again, you can use negatives if you want. You can say negative 1, 0, 1, and 2 if you'd like. You could even use decimals if you'd like, but I'm not going to because that seems like it make it more complicated than we want. So negative 1 times 2, that's negative 2 plus 6, that's 4. 2 times 0 is 0 plus 6 is 6. 2 times 1 is 2 plus 6 is 8. Yeah, you can see the pattern there of adding 2 each time, which is the slope on this one. So 2 times 2 is 4 plus 6 is 10. So the domain and range that I get from this, the domain is negative 1, 0, 1, and 2. And then the range, there in red, 4, 6, 8, and 10. And this is listed from least to greatest. And finally, number 9, whatever values you want to choose, negatives, decimals, fractions. I'm just going to say 0, 1, 2, and 3 on this. So I'd say, okay, 2 minus 3 times 0. You can put that in the calculator. It's still just going to give you 2. Or 2 minus 3 times 1. Right, that's what this one will be. 2 minus 3 times 1 there. Which, when you put in the calculator, should be negative 1. And then this next one, 2 minus 3 times 2, which should be negative 4. And then this last one, 2 minus 3 times 3, should be negative 7. Now the domain and range, again, I'm just going to point this out on the assignment. It wants these listed from least to greatest. And while the domain is fine, 0, 1, 2, and 3, the range is not, because it's listed from greatest to least, but it will want it from least to greatest. So let's put this as negative 7, negative 4, negative 1, and 2. So while they may not align with their corresponding values up and down, with domain and range, it doesn't matter. We look at these individually. So there's the domain and range for those, at least for the ones that I found. And there's our objective. I can write the equation for a function.